Good morning, everyone. Hope you're all doing well. So we had a test that ended yesterday midnight, covered 2 chapters, organics. We are now going to move into the very mild version of biochemistry. Okay, so the last 2 chapters have to do with more biochem stuff. This is by no means a comprehensive biochem course, okay? We're really gonna be just like super gentle with it. I would say both of these last 2 chapters are gonna be more definition based or memorization based than anything. So whereas a lot of the stuff in the past, I'm like, learn how to do the problem, understand the concept so that you can, in any situation, answer a problem, right? These 2 chapters are definitely more like, um, name 2 examples of polysaccharides, okay? And you would have two examples. Or, maltose has which type of glycosidic bond, and you kind of have that memorized. So we are going to start with carbohydrates, and then we'll get into amino acids next week. So, okay. So this is a woman, Paula. She's a diabetic nurse. She's teaching this other woman how to test her blood for glucose before and after a meal. Glucose is a certain type of carbohydrate that we have in our blood that provides us with energy, all right? Our bodies have a specific way of regulating that. Sometimes our bodies can't regulate glucose, whether it be genetics or diet or a combination of the two. So what is a carbohydrate? A carbohydrate is sort of an umbrella term for anything that's made from carbon, hydrogen, and oxygen. And it's a major source of energy in our diet. So you do need to have carbon, hydrogen, and oxygen in it. Sometimes these things are called saccharides, which is just a fancy way of saying sugar. So we can classify these monosaccharides. We'll do that a little bit later as aldehys or ketose. We'll do that in a minute. So an example of a carbohydrate that we already said is glucose. Glucose is produced through photosynthesis by plants. Thank you so much, plants, for doing this. So what they will do is, and it's like we get two things, like more bang for our buck here, because the plant takes CO2 out of the atmosphere, which isn't really useful to us in a respiratory sense. So they take CO2, they combine it with water, and then they take energy that comes from the sun, and they actually produce their own food. So through photosynthesis, they make glucose and they make oxygen. Both of these things are useful to us. So when we're cutting trees down and we're reducing the amount of vegetation, it's not just that we're getting rid of one of our oxygen sources. It's also that we're getting rid of like a huge food source for us and for other animals. The reverse process of this is known as respiration. So us as humans, animal life, we take oxygen from the air, we combine it with glucose that we consume, and then we produce energy, water vapor, and CO2. So hopefully now, after a little bit of chemistry, this isn't quite so scary of an equation, right? Maybe at the beginning of the semester that'd be a little freaky, but now you can start to see, oh, it's happening in forward and reverse. You know what some of these things are. This may be a little bit more intimidating, but we will get into that. So when we're dealing with a carbohydrate, we want to divide it into being either a monosaccharide, a disaccharide, or a polysaccharide. The simplest thing we have here is a monosaccharide. A lot of times these carbohydrates or these sugars, when they get in water, they'll like curl in on themselves and form a ring. This ring can uncoil into a sort of more of a straight chained carbon-carbon bond, but they do sometimes like to form these rings. So when you see these rings, we've got a string of carbohydrates or a string of carbons. So this is a carbon here, this is a carbon here, this is a carbon here, carbon here. We also have a carbon here, and then it's bonded to an OH here, and then there's a bond to the oxygen here, right? So that's a skeletal structure that we're seeing there. Do I expect you to replicate these structures with pen and paper? No. Okay. You will need to be able to sort of identify properties of these sugar rings. So anyway, a monosaccharide is one of these single sugars. It's a simple sugar. If I put this thing in water, there is no hydrolysis, and hydrolysis meaning would it like break apart? As you know, have started to learn now that like these carbon-carbon bonds are really, really strong. It takes a lot to break them apart. You would have to go through a process like photosynthesis or respiration. Just dropping them in water isn't going to do it. A more complex sugar is a disaccharide, which contains two monosaccharides. So sucrose or table sugar is a disaccharide of glucose and fructose. They have two of them and they're chained together and they've got this little bond right here. Okay, this is like an ether bond. When I drop this in water, it can break apart into simpler molecules, sugar molecules. And then down here, we've got what's known as a polysaccharide. It contains a bunch of monosaccharides. It's a long chain. If I put a bunch of water in here, we can get many individual molecules of whatever the simple sugar is that it's contained. So have you ever heard of, oh, instead of eating simple sugars, it's better to eat more complex sugars, or complex, instead of simple carbohydrates, complex carbohydrates? Something like this would be like fructose, okay? You're just, bam, you're getting the sugar ring. Real easy for your body to take that and convert it into energy. But we don't usually move enough to convert it all to energy. So a lot of times it's converted into stored fat. When you hear like, oh, eat something that's a complex sugar or complex carbohydrate, it's one of these long chain things, all right? Those tend to be more of like our starches or our like grains and stuff, whole grains. It requires your body to use energy to break it down into the sugar that it could even use. So this is just kind of a healthier way. You're not getting so much sugar, boom, all in your system all at once. So when we're looking at a monosaccharide, these things will range from about 3 to 8 carbon chains. And in the carbon chain somewhere, you're going to have a carbonyl group. So remember, a carbonyl group is where you have a carbon that is double bonded to an oxygen. Now, that carbonyl group could either be at the end of the chain, making it an aldehyde, al at the end, or it could be a ketone where that carbonyl group is somewhere in the center. If it's at the end, or if it's an aldehyde group, we will call that an aldose, or an aldose, sorry, or aldosis. So looking at this carbohydrate over here, I would say that's an aldose. If it's a ketone instead, so it's got that carbon double bonded to an oxygen somewhere in the center of the chain, we call it a ketose. So do you see how this is written? This is called a Fischer projection, how it's written, where the carbons are along the center line and then it has all the hydrogens and oxygens. This sugar, like this here, can wrap around and connect to this. that's what's giving it the cyclical shape. Okay, so you're kind of looking at this a similar thing. For this carbon chain, all of the carbons will have a hydroxyl group or an OH group. And then it'll have a hydrogen in its other spot. Because remember, carbon likes how many slots? 4 slots. Okay, so the only place that you won't have that hydroxyl group is on the actual carbonyl group. The reason being because you've got the double bond to oxygen, so it's been oxidized, so it doesn't have that hydrogen sitting there. So would I say draw ethros here? No, but I could say, hey, identify this as an aldose or a ketose. Okay, if it's at the end, aldose; if it's in the middle, ketose. As far as the names are concerned, monosaccharides can be classified by how many carbons are present. It's a little bit different than our organic naming though. So 3 carbons is triose, not pro. 4 carbons is tetros, like a tetrahedral. 5 carbons is pentose, 6 carbons is hexose. So an aldopentose, if you see it written like this, aldopentose, that is a 5 carbon saccharide, which has an aldehyde group. The aldo is saying that the carbonyl group's at the end, pent being 5. If I have a ketohexose, keto meaning that I have a carbonyl group somewhere in the middle of the chain, hexose being that there's 6 carbons. Do I explicitly say where that keto is, where the carbonyl group is? No, it's just somewhere in the middle. So again, I couldn't give this to you and you write an exact structure because there's quite a few things that could fall under the definition of a ketohexose. Okay, a ketohexose is a general term for a grouping of monosaccharides. So let's look at these guys here. These are a bunch of different monosaccharides. Over here, our buddy fructose. All right, fructose is a ketohexose. Look at the carbons. Let's count them out just so that we're not missing any. 1, 2, 3, 4, 5, and 6. They write the carbons in these structures here. This is, of all of these, this is the only keto, right? It's the only one that has it in the center somewhere or in the center of the chain. All the other ones are al at the ends, so they're aldose. This is an aldotriose, aldotetros, aldopentose, because there's 5 carbons. You feel good with that? That's not too mind-blowing. Yes, carbohydrates can get much more mind-blowing than that, but we're going to keep it simple. All right, so I want you to look at these 2 structures, and I want you to tell me, are they an aldo or a keto, and then tetros, pentose, or hexose? So like, for instance, it'd be a ketopentose. Okay, nothing crazy here. Probably the most involved part would be if you were like writing the structure out. But what do we got here on the left? Okay, where's the carbonyl group? It's that double bonded with the oxygen and carbon. So it's at the end. So this is an aldo. And we've got 1, 2, 3, 4, 5, 6. So this is an aldohexose. Over here, this is a carbonyl group in the center. So this is a ketone. So keto. And we've got 1, 2, 3, 4, 5. Ketopentose. So while we're looking at this, FYI, I think that the FYI, I think that the labs for this this chapter and the next chapter are awesome study guides. Okay, so use the labs. If you can get the labs, you'll be almost, you'll be like 95% there for the exam. So definitely work the lab. And speaking of, I'm going to open the lab so we can do a little bit of it together. If you want to open your lab as well on your computer, you can do that and make some annotations. The carbohydrates lab is going to be right here, and the amino acids lab are going to, so both of them are online. So let's click on that carbohydrate lab. I have the ability in here to draw directly on there. So identify each Fisher projection as an aldo or a keto, a triose, a tetros, a pentose, a hexose, and then we haven't done D or L isomer yet. We'll do that in a minute. But for now, I'm gonna have y'all do the first three, okay? If you see there's a cross at these points and there's no carbon written in, there is a carbon there, okay? So just, and why is the carbon at the end written in, but not those? I will tell you in a minute. But for now, just count up the carbons and let's just do that first part. Give yourself a little space in the front too, to put the D and the L in after. All right, so for this first one, it is carbon. Oh, well, let's find the carbonyl group. So it's on this one right here. Get comfortable with CHO being also symbolic of a carbonyl group. The carbon is double bonded to the oxygen. You kind of are supposed to know that just because you know carbon likes 4 bonds and then it's single bonded to the hydrogen. So we've got 1, 2, 3, 4. So that's a tetros, and it's at the carbonyl group's at the end. So this is an aldo tetros. Good with that? Any questions? If you do, just throw your mute off real fast. Okay, next one here, 1, 2, 3, 4 carbons. So this is also a tetros, but our carbonyl group is in the middle somewhere. So this is a keto tetros. We've got another one here. This is what, 1. We've got our, well, let's identify the carbonyl group. It's at the end. So this is an aldo. And it's 1, 2, 3, 4, 5, and 6. So this is an aldo hexose. There's a couple more for you to do there. We'll do these first 3 together. You feel good with that? That's not too intense. So let's talk about this D and L isomer thing. And then we can come back and fill those in. Okay, so what is a chiral molecule? Has anyone ever heard the word chiral or things having chirality? So a chiral molecule is pretty much when 2 things are a mirror image of each other. They look like each other. The things are arranged, they're stuck together in a similar way, right? Your fingers are, your hands, for example, are chiral structures. So your right and left hand, right? Your thumb is at the end. Your fingers are attached to the top of your hand, and your hand is attached to the wrist. That's true on both hands. But because of the way that they're set up, I can't superimpose them. And when I say superimpose, I mean I can't stack them in any way so that they are identical to each other. They are 100% unique in their shape. So like if you look at my hands in the image here, so if I have my hands facing you, the top of my hands, and I try and stack them on each other, what's going on? Are my thumbs matching up? No. My thumbs are on opposite sides. Okay, well, what if I flipped one of my hands? So I'm going to take my left hand and I'm going to flip it so that it's palm facing you and the back of my other hand. Now I'm going to stack them. Oh, look, the thumb matches and the fingers match, but it's a front of the hand facing you and a palm facing you. So there's no way for me to rotate these so that they become the same thing. They're like unique. A really good example, can you put a left glove on your right hand? No, it's designed specifically for the right hand, but they're both hands and the fingers are both like attached in a similar way. So atoms can have this as well, this thing called chirality, where they can't be superimposed. So I guess it's like backing us up a little farther here. So structural isomers. So molecules are structural isomers when they have the same formula, but are bonded in different arrangements. So this is not a chiral thing. This is like two different arrangements. So do you see how this formula and this is for both of these. So this is for C2H6O. They both have this formula, but look at this one. This is ethanol with the OH at the end. This one is diethyl ether with the oxygen somewhere in the middle, right? And the hydrogen stayed on the carbon at the end. So same formula, different bonding arrangements. That's considered a structural isomer. Here's another one, C3H6O. They have both of these things have the same formula. They have the same number of atoms, but they are placed in different ways. This is propanal. This is an aldehyde. This is propanone, a ketone. And they have different properties, right? Just by moving that over, it changes the properties of the material. So then we have these things called stereoisomers. Okay, stereoisomers are not the same thing as structural isomers. Stereoisomers have identical molecular formulas, so they're made of the same parts. The atoms are bonded in the same sequence, but differ in the way they are arranged in space. When the mirror image of an organic molecule cannot be completely matched, they are considered non-superimposable or they are classified as chiral. So stereoisomers are chiral things. Our hands are an example of a stereoisomer. They're made of the same bits, right? 4 fingers, a thumb, hand, and a wrist. They're arranged in the same sequence in the sense that, your thumb is on the end, your fingers are in the middle, they're attached to your hand, which is attached to your wrist. But they're arranged in space in a different way. My left hand has my thumb, in this case, pointing to the left. My right hand has my thumb pointing to the right. So that's what gives it this chiral property, or this inability to superimpose. Why does that matter? Because if it's a molecule, it means that they're two different things. Like I can't just like rotate it to make it the other thing. Will have slightly different properties. So here's our chiral hand. Here's, let's see if there's some things that we can look at that are chiral. Okay, gloves are a great example of chiral. Two bats are achiral, meaning I could move this and then superimpose it, right? It looks like a mirror image. I mean, it is a mirror image, but what if I just take this bat and I just move it over here? Then they're stacked on top of each other. Are they unique objects? No, they rotate in the same way. These are another example of achiral, right? If I move this glass here, they're stacking in front of each other. They will be mirror images. What about these shoes? Those are chiral. There is no way I can take this shoe on the left and rotate it or flip it or do anything so that it becomes the exact same shape as this shoe. That is why you can't put your left shoe on your right foot. So how can you classify something as a chiral? And specifically, you want to be looking for chiral carbons. So carbons that are non-superimposable. Molecules are considered chiral. The whole molecule is considered chiral when at least one or more of the carbons are chiral. A carbon atom is considered chiral. It is really this simple if it's bonded to 4 different groups. That doesn't mean 4 different buddies. It means 4 different actual groups, and I will show you that in a minute. This chirality of one of the carbons makes the molecule chiral, which makes the whole thing non-superimposable or makes them different. This is where this L and D isomer thing is going to come into play. So here is an example of a chiral carbon. So carbon is in the center. And look, it is bonded to 1, 2, 3, 4 different things. Okay. The mirror image of this thing is this over here. So here I have carbon bonded to a hydrogen, bromine, iodine, and chlorine. Do you see how they're like respectively in the same arrangement, right? It's not like the chlorine is attached to the hydrogen. The chlorine is still attached to the carbon, just like the chlorine is attached to the carbon. But they've swapped the place of 2 things. So these 2 things have switched. This and this swapped places, right? And this first one, the chlorine's on the left, or this first one, the bromine's on the left and the chlorine's on the right. Here, the chlorine's on the left and the bromine's on the left, chlorine's on the right, chlorine's on the left, bromine's on the right. And it's, you may be looking and think, well, aren't those the same thing? Couldn't I just rotate this and get the same structure? No, it's like those gloves. If you rotate the glove, it's still the right-handed glove. So let's rotate it. If I rotate it, the iodine will move to this spot here. The bromine will move to this spot here, and the chlorine will move to this spot here. Okay, iodine, bromine, chlorine. That is not the same thing as this. What if I rotated it again? You're never going to get it to a place where these 2 things can superimpose. They even took they have the image here, right? So they took this and they, it looks like they took this and they stuck it on top of here. So here's the chlorine. I'm sorry, here's the carbon. Here's the hydrogens. Those match, those match, those match. That doesn't match and that doesn't match. And there's no way to rotate it to get it to match. Why is that important? Well, because it's classified as 2 different things. Okay, when you have a chiral carbon, it's unique. It's got a unique imprint. So you need to tell the reader, are you dealing with this one or are you dealing with this one? These 2 things are called enantiomers. So they're non-superimposable. They have the same chemical formula. They have the same arrangement or attachment to adjacent atoms, but they are arranged in slightly different order. We call them enantiomers. This is an example of an achiral carbon. So here's the carbon. Is it attached to 4 different things? No, it's got a repeat here, right? It's got a bromine and a bromine. That repeat is what makes it achiral. Okay, let's get the mirror image of it. Can I rotate this thing to get back to the first thing? Yes, if I take this and rotate it like this, so move the chlorine here, the bromine and the bromine here, what do you get? You get this. Is that the same thing as that? It is, it's the same thing. That's just like the baseball bat. I can rotate it and get the same molecule or object. So identify each of these as chiral or achiral. I am going to go over these with you all. So the carbon here, is this chiral or achiral? Remember when I said it's the group, it's not just the adjacent atom? So we want to look at this whole attachment, okay? So that's its own unique thing. That's its own unique thing. Now, we're not just looking at carbon bonded to carbon, okay? We're looking at the whole group. That's its own unique thing. So let's put 1, 2, 3. And then this, we look at the whole thing is its own thing. Oops. Why am I putting 3? Let's put 4. So 4 unique things. This is definitely chiral. What about this carbon, just for fun? Is this carbon chiral? How many unique things is it attached to? It's attached to this big clunky thing, right? And then it's attached to 3 hydrogens. So that is not a chiral carbon. Right? If I was to expand this out, it would be carbon, hydrogen, 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 and then this whole mess. So we've got to repeat. Let's look at this guy here, this next one. Chiral or achiral. So look at the carbon. It's bonded to 1 unique thing, 2 unique things, 3. Oh, there's a repeat. Okay, so this would be achiral. This wouldn't have a unique enantiomer. How about this last one here? Chiral. It's really as simple as, is it 4 different things, different groups? The place that I see people trip up on with this is on this one. They'd say, you know, here's a carbon and they're like, oh, well, there's a chlorine, there's a hydrogen. Oh, here's a carbon and here's a carbon. Those are repeats. We don't just look at the carbon. We look at the entire like limb. This is a methyl, this is an ethyl. Questions on that? Okay, cool. Great. So when drawing a Fisher projection, which is that where they have the carbons going vertically and then the H's and the OH's going horizontally, a Fisher projection is attempting to make a two-dimensional representation of what is a 3-dimensional molecule. It places the most highly oxidized carbon group at the top. When it says that, it really means that it's taking the carbonyl group and pointing it towards the top, okay? So you'll see either the aldehyde pointing up or the ketone really close to the top. It uses vertical lines in place of dashes for a bond that go back into the page. So when we see a vertical line, you really want to think of that as like kind of pushing into the page. It uses horizontal lines to represent wedges for bonds. That's the thing that's coming forward. So the verticals are going back into the page, the horizontals are coming forward. So we get this sort of like zigzaggy structure. We're kind of looking at the molecule from above. So here is what an image of a dash line, a dash structure would be. So the dashes are going into the page, the wedges are coming out. So if you were to look at this, like we're sitting above the line of the carbons, this carbon is, you know, we could say like at your neutral place, these 2 carbons are sitting lower than this carbon, right? They're dropping down. This hydrogen and this OH is coming up towards your face. In a Fisher projection, instead of having to draw all these dashes and wedges, which are time consuming, they just let you know, hey, if it is vertical like this, you can assume it's dropping down into the page. If it's horizontal, it's coming up. Now we know, well, let's look, do you see the place where a vertical and a horizontal meet? There's no carbon written. That's because it's a chiral carbon. Chiral carbons, you don't write the C. The C's here and here are because those are not chiral carbons. So hopefully now you're seeing why there's nothing written there. If it's a chiral carbon, they won't write the C. They'll just have a crossing point. That has 4 unique attachments. This carbon is not chiral. How many unique attachments does this carbon have? 1, 2, and then this mess, 3. Only 3 can't be chiral. What about this carbon? It has this mess, and then it has 2 hydrogens and then an OH. The 2 hydrogens are the repeat. That's what makes it not chiral. Okay, so L and D isomers. This is the L isomer. These are like very, very similar structures. These are both I'm not good with these ones, glyceraldehyde. One is an L isomer and one is a D isomer. How do we classify it as an L or a D isomer? So it has to be in its Fisher projection ordering. Again, I'm not going to give you this name and have you draw this. So don't get freaked out by that. I would give you this thing and have you give me descriptions of it. Like it's a ketohexose. It's an L or a D. So how do we decide if it's an L or a D isomer? You go down to the lowest chiral carbon, so the lowest crisscross. So that would be this one and this one. You figure out where is the OH. If the OH is on the left, it's an L isomer. If the OH is on the right, it's a D isomer. That's it. L for left, D for, I don't know, the other one. And that's like all you're going to need to do for identifying L and D isomers. If the OH at the lowest chiral is to the left, it's L. To the right, D. So I want you to go ahead and tell me if those structures we were looking at earlier on our lab are L or D. Okay, so go ahead. For these 3, I want you to add an L or a D, and it'll be like, if let's say that this was an L, it would be L dash, and you'd stick it in the front. I'll give you 40 seconds because it is that fast to do these. Okay, so looking at this one, we go to the bottom crisscross, which is the lowest chiral carbon, and figure out where is its OH. Its OH on this side is to the right, so that's a D. D aldotetrose. If that OH had been on the other side, it would be an L. Okay, let's look at this one. Go down to the lowest chiral carbon. This is not a chiral carbon, so we don't look at that one. We look at the one that's a crisscross. The OH is on the left, so this is an L, ketotetrose. This one, let's go to the very bottom chiral right here. The OH is to the left. This is an L, aldehexose. And that's it. You feel good with that? Like you could do the other 2 on your own for the homework. So we've got D's and we've got L's. We've got ketos, we've got aldos, pentos, tetros, all those. So again, I would not give you this mess and say, draw me a Fisher projection, but I would give you a Fisher projection and say, hey, classify this as something. All right, so this is giving us another practice on mirror image. So look at these two groups. We've got group A, which is two different things, and group B, which is two different things. Tell me if they indicate which pair is a mirror image that cannot be superimposed. So is this pair something that cannot be superimposed, or is this a pair that cannot be superimposed? i.e., is this a chiral carbon or is this a chiral carbon? So it's really as easy as take a look at the carbon. Is it connected to four different things? This has a hydrogen, a bromine, a methyl, and a methanol. Four different things arranged in four different ways. These are mirror images of each other. So this is non-superimposable or an enantiomer. This thing down here, it's a chiral carbon. This thing down here has 1, 2, 3 unique things, and then we get a repeat. So this is not mirror images. This would be an achiral carbon. All right, look at these. Tell me if both of these are aldose, specifically 1, 2, 3, 4, 5, 6. So this is a aldehexose. Both of these are aldehexose. Just tell me if it's an L or a D. A is, I mean, they're very similar, right? But A has, when we go to the lowest chiral, it has the OH on the right. So that makes it a D. Here, the lowest chiral has the OH on the left. So that makes it an L. Voila. So these enantiomers in biological systems, many compounds in biological systems have only one enantiomer that is actually active. So if the atoms, if we have two like chiral carbons, and one is arranged in one way and one is arranged in the other way, the enantiomer, it won't work. Specifically with like enzymes in our bodies. There are certain enzymes that will plug into the cell receptor, click in. If you have the enantiomer, it won't click in. It can't match up to get into the receptor, so it will be inactive. That they do that a lot where they'll have like a beauty product or they'll have like a supplement, and it will have the enantiomer, not the actual one that you want. It will have its mirror image, and it renders it useless. Your body can't absorb it. It doesn't do what it needs to do. That actually happens quite often. And they say, we have active ingredients. Yeah, active ingredients that don't work for your biological receptors. So it looks something like this, right? Like we've got this complicated carbon group, and then there at the end of it, sticking off of it, is a carbon, and it has has four different things, right? So this is a chiral carbon. This is one, and then these unique things. This thing can come along and plug into, oops, I'm sorry, plug into the enzyme. So you get triangle, circle, square, bam. Well, if instead of triangle, circle, square, you get triangle, square, circle, the triangle match up, the square can't get in that hole and the circle can't get in that hole. The shapes don't match. This will not work. So it seems so like silly. You're like, oh, it's just two of them flip-flopped, but it actually does have an effect. There's a substance used to treat Parkinson's disease, which is L-DOPA. or L-dopamine, which is converted to dopamine in the brain, where it increases serotonin levels and it can help regrow neurons in the brain. The enantiomer of this is D-dopamine, and it just doesn't work. Like your body can't break this thing apart, can't use it to make serotonin in the brain. So L-dopamine will work for Parkinson's disease, D-dopamine won't. And it's like, so it seems so similar. It's really just one switch of the arrangement. So again, a lot of times for drugs that we use, only one of the enantiomers is actually active. However, for many years, drugs have been produced that will mix the enantiomers. And chiral carbon and chiral technology is something that they do a lot in biological sciences, trying to figure out ways of taking like inactive enantiomers and then like switching them or rotating them so that they are useful in drugs situations. Okay, so Fisher projections of monosaccharides. I feel like we already went over all of this. Come on now. So here are some Fisher projections of a couple different things. We've got glucose, galactose, and fructose. We are going to revisit these guys, talk about them quite a bit. Glucose and galactose are both aldehydes. Fructose is a ketone. Okay, so in a Fisher projection, it's a way to represent carbohydrates. You take the most oxidized group and you face it towards the top. So that means you take the carbonyl group and you put it at the top. Here we don't have a carbonyl group, we have a ketone, but we put this one closest to the top. We have the chiral carbons as intersections of vertical and horizontal lines. We show the H's and the OH's, and we place the CH2OH group at the bottom. This is the thing that's not chiral, okay? We can then classify it as an L or a D isomer, go to the farthest chiral carbon and determine if it's facing left or right, L and D. So here's L-ribose and here's D-ribose. I would not expect you to know that this is ribose, okay? I would say, hey, these are two ribose. Which one's the L, which one's the D? Or I would say, hey, name it as far as it being 1, 2, 3, 4, 5 carbons. So it's a pentose with an aldehyde, aldopentose. That I would expect you to do, not name it as ribose. So this is L because it's on the left. This is D because it's on the right. I feel like this is all repeat. So let's just keep moving. Here's mannose. Identify it as D or L. There's the OH. It's on the right. That makes it a D. Okay. Didn't realize there were so many slides for this. Identify the number of chiral centers. That I do want you to do. Okay, tell me how many chiral carbons are in this thing. It's really easy to identify them. It is two chiral carbons. When it's a Fisher projection, when it's drawn like this, the chiral carbons will always be the crisscross points. This has 3 partners, so it's not chiral. This has, it only has 3 partners. So yeah, it's not chiral. This has 4 partners, but 2 of them are hydrogens. So this is also not chiral. 1, 2 chiral centers. Identify it as D or L. Where is that OH? It's on the left, so it's in L. Are these looking a little less scary? Read them. So we are gonna go into some monosaccharides, really common monosaccharides. This is kind of where I'm talking about the memorization, okay? You do wanna know these things about glucose and fructose and maltose. So glucose, specifically D-glucose, which means if you were to draw this out and you had the OH group, it would face the right. It's found in fruits, corn syrups, and honey. It is an aldehexose with this formula, C6H12O6, okay? Aldehexose, that means it's got an aldehyde carbonyl group at the end. Hexose meaning it has how many carbons? 6. A lot of times glucose is also referred to as dextrose, and also blood sugar in the body. So when you're measuring your blood sugar, you're actually measuring how much glucose you have. Glucose, being a monosaccharide, is a building block for more complicated disaccharides and polysaccharides. It is a building block for sucrose, lactose, maltose, and polysaccharides like cellulose and glycogen. And we will get into those disaccharides and polysaccharides a little bit later. A lot of times people mix glucose and sucrose up together. They're like, glucose, sucrose, isn't it all the same thing? It's sugar, right? Sucrose is what we would consider table sugar. Okay, that is a mixture, not a mixture, it's a combination of glucose and fructose. We will talk more about that a little bit later, but the other component of sucrose besides glucose is fructose, D-fructose. This is obtained from sucrose. It is, instead of its buddy glucose, which is an aldehexose, fructose is a ketohexose. It has the same formula as glucose. It's C6H12O6, but its arrangement is different. So it's a structural isomer. It is the sweetest of all the carbohydrates. It's twice as sweet as sucrose itself. Okay, so when you're consuming glucose, it doesn't have that as much of a sweet taste. When you're consuming sucrose, which is table sugar, it's a mixture of this and this. So this is like cutting some of the sugar or cutting some of the sweetness. The sweetness is really coming from this thing. So what do we do in the United States of America? We take that sugar molecule and we break it up and we just take the fructose, because why would we want glucose? Let's just have the pure sweetness and put that in all of our drinks. So when you see high fructose corn syrup and things like that, it's because they've broken up the sucrose and they've just extracted the sweetest part of it. So honey here contains glucose and it contains fructose. Again, when we have high fructose corn syrup, they are just extracting fructose. They don't usually extract the fructose from honey though. It's too expensive. They'll extract it from corn. Corn has both of these and they'll just crop out the fructose. So looking at them, similar structures, what is the difference? They're both Ds too. So they both have that OH to the end, but you see how the carbonyl is at the end here and the carbonyl is just one in. That's the difference between glucose and fructose. Makes a difference in its sweetness level though. All right, there is another simple sugar that you need to know, which is galactose. And if that's ringing a bell with like milk, you know, lactose intolerant, it is derived from lactose. So D-galactose is an aldehexose. It also has the same formula. So all of these monosaccharides have this C6H12 6. It's not found free in nature, so this thing doesn't just float around on its own. It's obtained from the disaccharide lactose. Lactose being, you know, what you get, you can get it out of milk products. It has a similar structure to glucose, except for the OH on carbon 4. So carbon 1, 2, 3, 4. Okay, do you see how on carbon 4, this isn't classifying it as D or L. This is one up. The OH is pointing to the left here. Okay, put that in your memory bank, pointing to the left. Let's go back to our glucose. Here's our glucose. The OH is pointing to the right on the 4th carbon. That makes a difference. In a condition called galactosemia, an enzyme needed to convert galactose to glucose. So our bodies take this thing and they pretty much take that OH here and they like swing it over here. It's not just a rotation, that it has to go through a chemical process to make it glucose, and then our body uses that, right? So we can drink lactose, break it up into galactose, and then convert it to glucose. There are certain people that cannot convert galactose into glucose. They'll get sick. So glucose is in the body. We can measure it in blood sugar. Normal glucose in the body is about 70 to 90 milligrams per deciliter. A glucose tolerance test here measures blood glucose for several hours after ingesting it. So if you've ever had hyperglycemia or hypoglycemia, and you have to do a glucose test, or if you've ever been pregnant and you have to do this, and they make your third trimester pregnant body fast for 12 hours, and then they give you this sugary drink, and your glucose will spike, and then it'll come back down. If you're hyperglycemic, here's normal, kind of sitting in the middle. You'll have a little bit of a spike, but not too much. If you're hyperglycemic, you'll have a huge spike, right? Really high elevated sugar levels. If you're hypoglycemic, you will get a little bit of a spike, almost bringing you to normal, but then you'll drop back down again. If you're diabetic, you are usually hyperglycemic. This occurs when the pancreas is unable to produce sufficient quantities of insulin. Insulin is what breaks down this glucose here. If you don't have the insulin to break down the glucose, you will have really high levels of glucose in your body fluids, which can cause all these different symptoms: thirst, urination, appetite, all sorts of different things. In older adults, it can cause weight gain. If your diabetes gets really bad, if you have too much of this sugar, glucose floating around in your system, you can actually have to have like limbs removed and things like that. The opposite of like diabetic or hyperglycemia is hypoglycemia, which you don't hear quite as much about. But this is where you have low blood sugar, or your blood sugar decreases really quickly. This can happen if you have an overproduction of insulin by the pancreas. Dizziness, weakness, muscle tremors. A lot of times a diet can be prescribed that just sort of levels off your glucose levels, or has you eat higher protein and lower carbohydrates. This is something that, you know, people may experience from time to time, where your blood sugar drops and you get kind of like lightheaded and a little weak feeling. Okay, so this right here, draw the Fisher projection of D-fructose and L-fructose. I'm not going to have you do that. I would have you identify it as D or L. So D being on the right, L being on the left. I would not have you draw this. If you have a homework assignment where it says draw this, just reference what the fructose structure is and put it in that way. So now we have these Hawthorne structures of a monosaccharide. So the most stable form for a 5 and a 6 ring sugar is to form a ring. Okay. So don't get freaked out by that. It's literally, see this ring here? It's taking this and it's just rotating it to connect with itself. So these Hawthorne rings are produced when the carbonyl group and the hydroxyl group react on the same molecule. So let's look at the carbonyl group. So the carbonyl group is this thing here. The hydroxyl group is this thing here. So these are rather this guy here. So this thing and this thing will stick together to make a ring. Again, I'm not expecting you to draw these. I'm not expecting you to identify them as far as like, that's fructose. I wouldn't expect you to take this thing and convert it into a Hawthorne structure, right? It does go through the steps on how to do that. I don't want you to do that. So here it says how to draw it. Turn the Fisher projection clockwise, fold it in on itself, and draw the new OH. So it takes, again, I'm not going to have you do this. But for your information, here is an aldehexose. You drop it down. This would be considered the open chain. This OH and this thing are going to connect together. So we ring it up on itself and they connect, okay? And you get a cyclical structure. Not going to have you do that though. But you do need to identify properties of this. So one of the things is, I don't see it in the slides here. Trying to see, yeah, I don't see it in the slide here. So I will just give you this information. So these structures, they're all a type of hexose. I want you to classify it as a ketohexose or an aldehexose. I'm not going to have you do pentoses. It's just going to be keto or aldohexose. So 6 rings. So if it's a ketohexose, this is how you're going to remember it. It looks like a house. Okay. So key to the house. So if it has a little steeple point at the top and it drops down to make a roof, that's a ketohexose. Aldehexose is the one, I don't know, it kind of looks like a boat. Okay. Al in a boat. I don't know. Aldehexose. That is the extent of, well, we're going to do an alpha and a beta, but that's the extent of like naming it. I wouldn't expect you to know that this is fructose or anything like that. So if it looks like a house, it's a ketohexose. If it looks like not the house, it's an aldehexose. So looking at this one here, what would we say this is? Number 8. It looks like a house, key to the house, ketohexose. This one here, this is the boat shape. So this is an aldehexose. If you're thinking, wow, I feel like this gets much more complicated than this. It definitely does. That's why we're keeping it pretty simple. You see this one here, number 10? This is 2 monosaccharides connected together. We call this a disaccharide, okay? So sorry, the options at the top were a ketohexose and aldehexose or a disaccharide. You don't need to name it as an aldose or a keto. You just call it a disaccharide. If you wanted to get curious though, looking at these 2 monosaccharides, this one looks like a key, or I'm sorry, this looks like a house. So this would be a ketohexose. This one looks like the boat. So this would be an aldehexose. If you're curious, this disaccharide is sucrose. This is our fructose and this is our glucose. So on top of being able to label it as a ketohexose or an aldehexose in the ring shape, you need to be able to classify it as an alpha or a beta form. How do we do that? I'll show you here. So you go to the carbon that is the chiral carbon to the right. So this carbon here, this carbon here. If the OH points down, it's alpha. I know that's weird because usually when we think of alpha, we think of above or over. But in this case, if it points down, it's alpha. If the OH points up, it's beta. Both of these are D-galactose. I will tell you right now, you can't look at this structure and determine that it's a D. That would be something that would have to be given to you. So this is an alpha, this is a beta. pointing down, alpha pointing up, beta. So let's go back to that set of Hawthorne rings that we had. See if we can classify them. You all seen how this is sort of kind of like a lot of this is just memorizing it, just memorizing the rules. So this first one, we go to the carbon, the chiral carbon all the way over to the right, not this carbon, because that's not chiral, this one here. What is the OH doing? Is it pointing up or down? It's pointing down, down being alpha. So this is an alpha ketohexose. What about this guy here? We go to the chiral carbon to the right. It is pointing up. That makes this a beta, the beta aldohexose. This one here is pointing down. So this is also an alpha ketohexose. Both of these things, this one, this first one, and this third one here, are both alpha ketohexose. But they're different structures. If you want to see here, both of the OHs are pointing down here. In this structure, one OH is pointing down, one OH is pointing up. So that's what makes these two different things, but we would classify both of them as alpha ketohexose. This last one here, where is that chiral carbon to the right? What's the OH doing? It's pointing down. Down is alpha aldohexose. The disaccharide, you won't give it an alpha or beta. We just call it a disaccharide. So for Fisher projections, you need to be able to tell me if it's a pentose, triose, tetrose, pentose, hexose, if it's an alpha or an aldo or keto, and if it's D or L. For the Hawthorne ring, I'm only going to give you hexose structures. I'm only going to give you 6 ring structures, okay? So you have to tell me if it's a ketohexose or an aldohexose. It looks like a house, it's the key. It looks like a boat, it's an aldo, and then alpha and beta. Try not to mix these up with the Fisher structure identifiers, okay? Again, if you wouldn't be able to tell me that this is a D or an L ketohexose from this structure. I would have to tell you that. The D and the L is something that you identify off of the Fisher projection. Oh, hello. 909. Okay. Any questions on that? No, this lab is totally golden. I love this lab for studying for students. It's pretty, I would say this lab is pretty much a study guide. So use that when you're running through stuff. The end of this lab too is all like matching definitions, which you will need to know that stuff. So yeah, it's great. We will finish up this chapter next week, moving into some properties of monosaccharides, and then we'll get into polysaccharides, disaccharides and polysaccharides. So we will stop there. Let me know if you have any questions, general throw out there, personal stay around. And I will see you all on Thursday. Bye, guys.